Well, you see, I keep circling around this question, and perhaps you've felt it too. What if the universe is quietly reminding us that calm is not just temporary, but also borrowed? And imagine it with me for a moment. This great ancient stone drifting through the dark, older than anything we've ever carved into memory. And it will slip so close to us that it moves beneath the ring of our own satellites. So doesn't that make you pause and, well, doesn't it make you wonder how something so vast, so silent, can wander into the fragile machinery wrapped around our little world? You know, I suppose when people talk about interstellar visitors like 3i Atlas, there's always that spark of excitement, but the real story might be unfolding much closer to home. On April 13th, 2029, Apophis will skim past Earth at roughly 30,000 kilometers, not just closer than the geostationary belt, but also close enough to make every model we trust hesitate for a heartbeat. And that's the thing, it's not just a flyby, it's a moment when all our assumptions might shift might shift ever so slightly, and that slightness can echo for decades. I suppose what fascinates me is how the universe works in these delicate ways. A tiny shift in sunlight, a faint tug from Earth's gravity, the smallest rearrangement of dust on a tumbling surface, not just little things, but also forces that ripple outward across years. And if you listen closely, moments like 2029 feel less like threats and more like invitations. Invitations to pay attention, invitations to breathe with the cosmos. Before we go on, I'd like to ask you to subscribe to the channel and leave a like. My aim here is simple, to help you drift off to sleep while exploring the wonders of science. Where are you on the map? Let me know where you are in the world and what time it is in the comments. It's always fascinating to see who's joining us from all around the world. So let's continue. Well, to begin unfolding this story, let me take you gently into the scale of what is about to happen and why so many scientists find themselves staring at their simulations late into the night, whispering numbers as though they are trying to calm a restless universe. You see, when we talk about a 340-meter wide object, we are not just talking about a rock. We are talking about a relic of the early solar system, a shard of time itself, shaped by billions of years of sunlight, collisions, and quiet drifting. And when something like that approaches Earth, not just closely, but also intimately enough to pass inside the region where our own satellites orbit, it forces us to rethink what is ordinary and what is extraordinary. So let us picture this moment carefully. The space around Earth is not empty. It is layered, structured, almost architectural. Low Earth orbit is where the International Space Station drifts, only a few hundred kilometers above us. A little higher, there are navigation satellites, scientific instruments, weather observers. And then far out, compared to the thin veil of atmosphere hugging Earth, lies the geostationary belt, a ring where satellites circle at just the right speed to remain fixed over one spot on the planet. That belt has become one of the most valuable pieces of real estate humanity has ever claimed in space. And beyond that ring, we imagine safety, we imagine distance. We imagine that anything approaching Earth would surely pass far above it. But Apophis? Well, Apophis breaks that illusion. The path it will take in 2029 dips below the geostationary ring. It slips underneath the satellites that beam our conversations across oceans. It threads the needle between Earth and the machines we have placed around Earth. And that reality is not just fascinating, but also humbling. The, the space we think of as ours, the space we treat as though we have domesticated it, is revealed in an instant to be fragile, temporary, and shared with ancient travelers. You see, when I say that no object of this size has ever been observed passing this close in the age of modern astronomy, I am not exaggerating for dramatic effect. We have tracked many near-Earth objects, and we have watched comets and asteroids skim by at safe distances. But it is rare to encounter an object of this scale slipping through the region of space where our technological presence is strongest. And that creates a very specific kind of awe. Not fear exactly, but a recognition that we as a species have only recently stepped out into the cosmic garden, and we are still learning how unpredictable the natural world can be. And, well, I suppose one of the most remarkable things about this upcoming encounter is that many people will not even notice. The public perception of near-Earth objects has shifted in strange ways. Some people imagine catastrophic impacts from films where an asteroid becomes a symbol of destruction. Others have grown numb because nothing bad has happened in their lifetime. And that disconnect between scientific significance and public perception is one of the reasons events like this feel so quietly monumental. It is not that the danger is imminent. It is that the encounter is unprecedented. It is that we are watching ancient physics interact with human technology in a single delicate moment. The question we often ask is why people underestimate something like this. Perhaps it is because the numbers are too large to grasp. 30,000 kilometers sounds far. The Earth is wide. The sky feels endless. And without a sense of the machinery orbiting above us, without the mental image of fragile satellites drifting in, predictable arcs, it becomes difficult to sense danger or wonder. But if you close your eyes for a moment and imagine that stone passing under the geostationary belt, you start to feel the narrowness of the gap. You start to feel how the Earth and Apophis are briefly part of the same choreography. Well, to think about it in another way, imagine watching a great bird glide over the surface of a lake. The reflection shifts, the ripples form. The water remembers that something passed close, even if nothing touched it. That is how Earth will experience Apophis, a silent gliding, a brief presence. A memory etched into gravitational fields and seismic instruments. And in the days after, scientists will gather the data, trace the orbit, and compare what they expect with what has changed, because something will change. And that is part of why this event matters so deeply. It is not simply the physical closeness that is unique. It is the opportunity. It is the ability to measure forces that are normally too subtle to detect. The tidal stretching from Earth, faint but present, the way the asteroid rotates, whether it tumbles, whether dust shifts on its surface, all these details influence the orbit, and all these details define the future. And when you consider how even a tiny shift today can become a massive shift decades from now, the importance of this moment becomes clearer. Scientists often talk about forcing functions, the small nudges that shape long-term trajectories. Apophis will receive many such nudges during the flyby. Not powerful ones, not dramatic ones, but precise ones. And, well, precision is everything in celestial mechanics. 1 millimeter per second is the difference between safety and alarm. 50 years from now. One handshake with Earth's gravity is enough to change a future encounter. It is not that Apophis is destined to strike us. It is that we need to understand what happens in 2029 to predict what comes after. And perhaps the most compelling part of this chapter is the image of Apophis itself. You know, when we picture an asteroid, we often imagine a smooth stone flying through space like a skipping pebble. But the reality is stranger. Many asteroids of this size are rubble piles, loose collectives of dust and boulders held together by gravity more than by strength. They drift through space like floating ruins of ancient worlds. When one of these rubble piles passes close to Earth, it is not just orbit that changes, but internal structure. A rock may shift, a void may collapse, a boulder may roll from one face to another, and every shift affects how sunlight heats the surface, which affects how the asteroid radiates infrared heat, which affects the direction of the tiny push known as the Yarkovsky effect. And, that tiny push influences long-term orbit predictions. So when we say that 2029 is an unprecedented event, we do not simply mean it is close. We mean it is revealing, it is instructive. It is as though nature has given us a rare chance to observe an asteroid in a natural laboratory. Earth becomes a tool, a gravitational lens, a sculptor of trajectories, and we have to watch closely because the lessons are subtle. The psychological effect on humanity is equally interesting. For centuries, we have looked at the sky and imagined threats. Comets were omens, meteors were messages. But now we look at the sky with equations in our hands, with satellites overhead, with telescopes that pierce the darkness. And yet, even with all our tools, we still face uncertainties. We still face the delicate chaos of an object dancing near Earth. It is not fear that this creates, but humility, a recognition that our technological world is suspended in a cosmic environment we barely control. And if you think about communication and media, you can see why the public often misunderstands. If a scientist says an object will pass safely but needs to be monitored, some people hear only the word safe. Others hear only the word monitored. It becomes difficult to convey the beauty of precision, the elegance of measuring forces too small to feel. But events like the Apophis flyby allow us to tell deeper stories, not just about asteroids, but about how we learn, how we prepare, how we grow wiser through observation. Well, as we drift further into the topic, you might start to sense that understanding the scale of 2029 is not just about distance. It is about the entire environment surrounding Earth. The rings of satellites, the magnetic field, the tides, the gravitational harmonics, all of these layers connect us to Apophis during its approach. And in the next part of the story, we will step into the realm of forces themselves, the quiet tugs and stretches that Earth exerts on anything that wanders too close, the tidal forces that do not roar like ocean waves, but still reshape the world of rock and dust. And, that is where our journey naturally leads us next. When we last left that drifting giant, Apophis, we were standing on the edge of a thought, hovering between the scale of its approach and the deeper question of what Earth itself does to a visitor that wanders too close. And this is where the story turns inward into the quiet mechanics of gravity, into forces that are not loud or violent, but gentle, stretching, shaping, whispering their influence across the body of a passing world. You see, tidal forces are not just the rise and fall of the ocean, they are the language planets speak when they meet other celestial travelers. So, so let us step into that language for a moment. Imagine Apophis approaching Earth, not just passing swiftly by, but moving through a gradient of gravity, a landscape of invisible slopes and curves. The side facing Earth feels a slightly stronger pull, the far side feels slightly less. And this difference, tiny though it seems, stretches the asteroid, tugs it, presses it. On Earth, we feel this as high tide and low tide. In space, an asteroid feels it as a slow rearrangement of its own interior. And if that asteroid is not a solid monolith, but a rubble pile, a fragile congregation of boulders and dust held together more by gravity than strength, then the effect becomes far more interesting. You see, the structure of a rubble pile is loose. The stones rest against one another like old ruins, balancing through mutual support rather than rigid bonds. When Earth's tidal field pulls on such a body, the stress does not propagate through the entire structure. Instead, it concentrates in pockets, in gaps, in fault lines of loosely settled rubble. And that means even a small tidal force can cause subtle shifts. Not dramatic ones, not catastrophic ones, but shifts that change the asteroid's shape ever so slightly. A boulder slides half a meter, a cavity collapses. A shallow ridge relaxes into a smoother slope. And, well, that is the quiet drama scientists are so fascinated by. It is not just what Apophis does to Earth's orbit, but what Earth does to Apophis's body. Because if the shape changes, the way sunlight heats it changes. If the rotation twists, the direction it re-radiates heat changes. And if these change, well, its long-term path shifts too. It helps to think of tidal forces as sculptors. They do not carve with chisels. They nudge with gravity. On moons like Io, the tidal forces from Jupiter are enormous, generating volcanic activity. On tiny bodies like Apophis, the effect is smaller, subtler, but the principle is the same. Stretch a body repeatedly, and the energy dissipates internally. That dissipation can become heat, motion, rearrangement. And when Apophis swings past Earth in 2029, the tidal stretching will be stronger than anything it has experienced for thousands of years. Perhaps longer. Its long wandering through the solar system has likely brought it near planets before, but never this near, and never near a planet as massive as Earth. So the encounter becomes a kind of stress test, a natural experiment, where the internal structure of the asteroid is revealed by the way it responds to gravitational pressure. What fascinates dynamicists is how sensitive the asteroid might be. If Apophis is more loosely bound than we think, it might deform noticeably, not to the eye, of course, but in the models, in the internal forces, in the rotational behavior. If it is more rigid, the deformation might be small, but still sufficient to alter the thermal inertia on parts of its surface. And even these small alterations can cascade over years. The Yarkovsky effect, that tiny push caused by infrared radiation, depends on the rotation, shape, and thermal properties of the surface. Change any one of these and, well, the future trajectory begins to drift. The idea that something as gentle as Earth's gravity could change the fate of an asteroid may sound strange. We grow older, clocks tick, and we imagine the universe unfolding in grand gestures. But gravity is patient. It works over centuries, over millennia. over orbits that trace paths through the inner solar system with delicate repetition. And an alteration of a few micrometers per second now becomes kilometers after decades. That is why tidal forces have to be understood not just in the moment, but as part of a long unfolding. Well, if we look deeper into simulations, the picture becomes even more intriguing. Some models show that for rubble pile asteroids, even mild tidal stress can cause landslides on the surface. Dust shifts downward, larger rocks slump. The redistribution of mass changes the moment of inertia. And when that happens, the asteroid's spin rate may change slightly. It might speed up. It might slow down. It might even enter a tumbling state, a chaotic rotation that complicates everything from thermal modeling to orbit predictions. The remarkable thing is that the tidal force involved is not enormous. Earth is not tearing Apophis apart. This is not the Roche limit where moons are shredded. It is something gentler, something that works, because the asteroid itself is delicate. And if Apophis is a rubble pile, then it is like a great sleeping animal being nudged awake. It stirs, it shifts its weight, it changes posture. And, those changes matter. Scientists have run countless simulations, not just to understand the interior, but to prepare for what might happen after 2029. And what they find again and again is that small deformations can lead to long-term divergence. Some scenarios predict that Apophis may begin rotating slightly faster. Others predict a shift in the spin axis. Others still suggest it could relax into a new equilibrium shape. It comes down to the details of the internal structure, whether it is cohesive or fluffy, whether it contains voids or larger boulders, whether its surface is coarse or fine. And these details matter because after the flyby, when scientists measure the new orbit, they will not simply compare positions. They will compare the entire dynamical personality of the asteroid. They will ask how the thermal forces have changed, how the resonances interact with Earth, how the gravitational harmonics respond. They will look not just at the orbit, but also the internal evolution. Well, you might wonder why all this subtlety matters to us here on Earth, why we care if a rock shifts by centimeters on a body that never touches us. The answer lies in how deeply we rely on prediction. Near-Earth object research is not about the moment, it is about decades from now. So tidal forces change the spin rate by a tiny amount, then 20 years later, the accumulated deviation becomes significant. It is not fear, but precision that drives this attention. There is another layer to this story, one that makes the tidal interaction even more compelling. Apophis's trajectory takes it through shifting gravitational gradients, not just from Earth, but from the Moon. The Earth-Moon system creates a complex field, a subtle interplay of pulls. And as Apophis passes between these influences, the stresses across its body change dynamically. It is not a single stretch, but a sequence of them, like a tide that oscillates during a storm, rising, falling, rising again. The combined effect can amplify internal rearrangement. There is a poetic side to this too. The same tidal forces that lift the oceans, that sway the crust, that govern the dance of Earth and Moon, reach out into space and touch a wandering rock, reshaping its destiny. It's not out there, it's in here, written into the same physics that governs the tides beneath our feet. And if Apophis responds sensitively, it may emerge from the encounter slightly altered, a body with a new spin, a new vibration, a new resonance. And scientists will look at those changes not with alarm but with admiration, because they reveal the hidden physics of rubble piles. The flyby becomes a laboratory, an experiment we did not design but are fortunate enough to witness. As we follow this thread further, it becomes clear that tidal forces are not just a chapter in this story, they are a bridge. They link the raw scale of the encounter to the deeper uncertainties that come next. Because once Apophis is reshaped, even slightly, the assumptions that underpinned older models begin to slip. And, well, that leads us directly into the realm of scientific assumptions themselves, into how we build predictions, how we measure what we cannot touch, how we trust data that may be older than the transformations to come. And that is where the next chapter naturally begins, with a quiet but important question. What happens when the foundations of our models shift beneath us, even by the smallest amount? Well, when we step from the realm of tidal forces into the quiet architecture of scientific prediction, we find ourselves confronting something far more delicate than gravity itself. And that is the uncertain foundation on which every orbital model stands. You see, when we predict the path of an asteroid like Apophis, we are not just drawing a line through space. We are tracing a story built on assumptions, on values we choose because they seem right, because they fit within the limits of our measurements. But, what happens when one of those assumptions shifts, even slightly, after a close approach like the one in 2029? It is not just the numbers that change, it is the future itself that bends. To understand this, imagine a model of Apophis sitting on a scientist's screen, a shape rotating, a trajectory plotted, a set of parameters beneath it that describe its mass, its density, its reflectivity, its spin state, its surface roughness. All of these numbers are estimates. Some come from radar, some from light curves, some from thermal models, and, well, each has a range of uncertainty, a quiet shadow beneath the value itself. When we say Apophis is this massive or spins at this rate, what we really mean is that given our data, this is the most reasonable approximation. But the universe does not care about approximations. It follows the real values. And that creates the fragile tension in asteroid prediction, because the models we trust depend on the truth matching the numbers we assume. And in many cases, especially with rubble piles, the truth is far more complex than what our instruments can see. Well, let us consider mass. It seems simple. How heavy is Apophis? But we do not put asteroids on scales. We infer mass through gravitational interactions, through how radar echoes return, through thermal properties. And those inferences depend on assumptions about shape and density. If Apophis contains voids, as rubble piles often do, the density decreases. If it contains large internal boulders, the density increases in pockets. So the value we use in models is not a certainty, but a best guess. And if tidal forces in 2029 shift that internal structure even slightly, redistributing material, then the mass distribution changes. Not by much, but enough to matter. The rotation rate is another assumption with hidden fragility. We measure how fast Apophis spins by watching the way sunlight reflects off its surface, the flicker in brightness. But if the surface shifts after the flyby, the pattern of reflection changes, and so does the inferred rotation. If the asteroid starts tumbling, the change becomes even more complex. And because the rotation influences how the asteroid absorbs and emits heat, a small misunderstanding here can lead to predictions that drift over decades. You see, reflectivity or albedo is another subtle player. The way sunlight bounces off the asteroid depends on the smoothness of the surface, the mineral composition, the slope of boulders. After the tidal pass, dust redistribution might expose darker layers or cover reflective ones. And even a slight change in albedo modifies the thermal forces acting on the asteroid. These thermal forces are tiny, but not just tiny, but also continuous. They push gently, day after day, orbit after orbit, shaping the long-term path. And, well, then there is the shape itself. Perhaps the most deceptive of the assumptions, we imagine Apophis as a certain form because radar images show us a rough silhouette. But radar cannot see every cavity, cannot map every ridge, cannot reveal every internal void. The shape we model is a simplification, a useful one, but a simplification nonetheless. And the effect of shape on the dynamics is profound. The way the asteroid radiates heat depends on its contours. The way it responds to gravity depends on its mass distribution. The way it rotates depends on its moment of inertia, which depends on internal structure. So when we look at the models predicting the path of Apophis decades into the future, what we are really looking at are trees of possibility, branching structures. If this assumption is slightly wrong, the path shifts this way. If that assumption changes after the flyby, the path shifts another way. And the deeper you look into this, the more you realize how sensitive the predictions become. It's not out there. It's in here, in the way we build knowledge, in the way we trust numbers that hold within them the uncertainty of observation. Well, scientists acknowledge this openly. They publish papers detailing the limits of the models, the ranges of uncertainty, but the public often hears only the headlines. Safe for 100 years, no impact risk. And while these statements are true, given the models, they do not capture the evolving nature of the asteroid itself. Because after 2029, the parameters we currently use may no longer be valid. They may shift, they may broaden, they may require recalibration. Think of it like predicting the path of a leaf on a stream. If the leaf were rigid, smooth, predictable, the prediction would be straightforward. But if the leaf can warp slightly, or curl, or absorb water, then the future path changes. Not because the stream changed, but because the leaf did. Apophis is like that leaf. The solar system is the stream. And the tidal event of 2029 is a moment when the leaf absorbs water, shifts shape, changes the physical parameters that determine its drift. You know, it is tempting to imagine that with modern technology, with deep space tracking, with powerful computers, the prediction should be perfect. But perfection is not how science works. It's not certainty, it's refinement. It's not final answers, it's better answers. And the predictions improve with each new observation. This is why dynamicists continue to publish new models, adjusting values, exploring the full range of possibilities. It is not alarm that drives them, it is honesty. And, well, part of this honesty is recognizing that after the flyby, the uncertainties may widen before they narrow. Because the asteroid may do something unexpected. It may shift more than anticipated. It may enter a new rotational state. It may reveal that some of our assumptions were slightly off. And this does not create danger. It creates opportunity. the opportunity to measure again, to refine, to rebuild models with updated information. The beauty of orbital mechanics is that it is both precise and chaotic. Precise in the short term, chaotic in the long term. Sensitive to initial conditions, sensitive to the very assumptions we are discussing. And in the case of Apophis, the flyby acts as a reset point, a moment after which the previous predictions must be revisited with fresh data. Well, consider the reflectivity again. If the surface darkens due to dust movement, the asteroid absorbs more sunlight, heats unevenly, and emits more infrared in certain directions. That changes the Yarkovsky drift. Or consider density distribution. If a cavity collapses, the center of mass shifts slightly. That shift affects rotation. Rotation affects thermal balance. Thermal balance affects orbital drift. So a small change in any parameter ripples outward like a slow-moving wave across decades. This cascading sensitivity is why the scientists studying Apophis never fully stop analyzing, never fully stop updating models. Even though impact probabilities are currently ruled out, the continued research ensures that if those probabilities ever change, we will know with precision. It is not just protection, it is understanding. You know, there is a philosophical side to this too. We grow older, clocks tick, and we imagine the universe as a place governed by perfect predictability. But the deeper we look, the more we see that predictability is not just about knowing the laws of nature, it is about knowing the initial conditions with perfect clarity. And that clarity is always evolving, always improving, always limited by the precision of our instruments. And this is where the next bridge in the story appears, the one that connects the assumptions we build to the forces that shape the cosmos in the smallest ways. Because if tidal forces can shift the asteroid, and if assumptions can drift, then the next force we must explore is the one that amplifies these tiny alterations across time. The force that turns heat into motion, warmth into drift, sunlight into trajectory. And that next force is the Yarkovsky effect, the quiet push that can change the fate of worlds. Well, when we arrive at this next part of the story, standing right where the subtle interplay of heat and motion begins, we find ourselves drifting from gravity's pull into something even quieter, even more delicate. And that is the Yarkovsky effect, a force so small that at first it feels almost imaginary. But it isn't imaginary. It is real. It is persistent. It is the kind of force that quietly rewrites the future one warm photon at a time. So let us step slowly into it, like walking into a room where sunlight shifts across the floor, reshaping everything without ever making a sound. You see, the Yarkovsky effect begins with warmth. That is all. A rock in space absorbs sunlight during the day, heating up bit by bit. And as it rotates into night, the rock cools down, releasing that heat as infrared radiation. Each photon that leaves the surface pushes back just a little, like the softest exhale, and, well, the cumulative push changes the asteroid's orbit, not just slightly, but also consistently. Over years, over decades, over centuries, what seems like nothing becomes something. And that is the strange beauty of it. It's not out there, it's in here, in the way surfaces breathe warmth into the void, in the way the simplest thermal process can shape the path of a world. Well, imagine Apophis spinning through the sunlight. One side heats up and cools later. The exact timing of that cooling decides the direction of the push. If it cools, In the afternoon of its rotation, the radiation pushes in one direction. If it cools closer to local sunset, the direction shifts. And the tiniest difference in timing creates a different force vector. The rock's rotation rate matters, its orientation matters, the roughness of its surface matters, the mineral composition matters, the heat capacity of the dust grains matters. And when you bring all these things together, the Yarkovsky effect becomes not a single force, but a symphony of micro forces, each shaped by the asteroid's personality. Now consider everything we learned in the previous chapters. Tidal forces in 2029 may alter the surface slightly. A boulder might tumble from a ridge. Dust may migrate to a new resting place. The rotation axis may tilt by a few degrees. Each of these changes reshapes the thermal environment. And that means that whatever Yarkovsky force Apophis experiences before 2029 might not be the same force it experiences after it. This is why scientists watch the flyby so carefully. They know that even a small rearrangement can amplify through the Yarkovsky effect, nudging the orbit gradually into a different long-term trajectory. Well, let us take a closer look at how it works. When sunlight strikes the asteroid, the heating is not uniform. Craters trap heat, ridges radiate it quickly. Smooth regolith cools at a different rate than rough boulders. And, when Apophis rotates, the warmed regions shift across its surface like glowing embers. The thermal lag, the delay between heating and cooling, determines the direction of the net push. If the asteroid spins prograde, the radiation tends to push it outward from the Sunday. If it spins retrograde, the radiation tends to pull it inward. And if tidal forces alter the rotation state, even slightly, the long-term drift can reverse direction entirely. It is almost poetic to think that sunlight can move mountains in space. Not just move them, but guide them, shape them, define the arc they take through the solar system. You see, the Yarkovsky effect is especially influential for bodies around a few hundred meters wide, too small to resist the thermal push, too large to warm uniformly. Apophis sits in this perfect range. The push is small but not negligible. It is slow but not trivial. And over the course of years, it moves the asteroid by hundreds of meters, over decades, kilometers, over centuries, thousands of kilometers. And that can mean the difference between missing Earth or striking it in some far future scenario. Well, this is why the surface roughness matters so much. A rough surface absorbs more heat and radiates it differently from a smooth one. A surface coated in fine dust behaves differently from a surface covered in boulders. And if tidal forces in 2029 cause even 1% of the surface to shift, the thermal map changes, the way heat flows changes, the direction and magnitude of the Yarkovsky push change, and the predictions for future encounters must be updated. Scientists run simulations with different thermal inertia values, surface textures, and rotation states. And, they find that a small change in roughness can alter the orbital drift significantly. That is what makes the Yarkovsky effect one of the most challenging forces to measure. It hides in the details. It hides in the dust, in the shadows, in the microscopic texture of stones warmed by sunlight. It's not certainty, it's refinement. It's not the dramatic forces, it's the subtle ones that matter. Another interesting part of this story is how the Yarkovsky effect interacts with spin rate. If the spin accelerates, the thermal cycle shortens. If the spin decelerates, the cycle stretches. And if Apophis begins tumbling after the flyby, the thermal pattern becomes chaotic, making long-term predictions incredibly difficult. The asteroid's surface would warm irregularly, the push would vary unpredictably, and the models would have to treat the future as a cloud of probabilities rather than a line. Well, imagine holding a stone in your hand. You warm one side and it radiates heat. But if you roll it in your palm, slowly or quickly, the warmth spreads differently. And if you toss it in the air and let it spin chaotically, the warming becomes unpredictable. The Yarkovsky effect responds to these changes intimately, faithfully, almost eagerly. You see, scientists have observed this effect in other asteroids as well. Some drift inward over decades, some drift outward, some flip direction after surface changes caused by close passes or impacts. And these observations teach us that the Yarkovsky effect is not a single predictable phenomenon, but a sensitive web tied to every physical detail of the asteroid's body. The most subtle challenge is that the effect is incredibly hard to measure directly. You cannot look at an asteroid and see the thermal radiation pushing it. You can only observe the orbit over the course of many years and detect the drift. And even then, the drift must be separated from gravitational influences, resonances with planets, and measurement uncertainties. So by the time you detect the Yarkovsky drift with confidence, the asteroid may have already changed slightly, especially if a flyby has occurred. Well, this brings us back to 2029 and the tidal encounter. If the flyby changes the surface of Apophis in an unpredictable way, the Yarkovsky effect may shift too. And the predictions for the decades that follow will have to be recalculated, not because of danger, but because the asteroid has changed. The future path is not fixed, it is malleable. It is shaped by warmth as much as by gravity. This interplay between thermal physics and orbital mechanics reveals something profound about the cosmos, that small forces matter, that quiet processes shape worlds, that the future is not written in the bold strokes of planetary dynamics alone, but in the soft strokes of sunlight warming dust. And, this brings us to a deeper realization. Once the assumptions change, and once the thermal forces shift, the predictions must widen. And when predictions widen, the gravitational landscape becomes more complex. In particular, small changes in drift can alter how an asteroid encounters gravitational resonances, tiny corridors in space that can redirect a body toward a future encounter. So as we leave the world of heat and radiation behind, we find ourselves stepping toward gravitational intricacies that are even more delicate. Narrow windows in space, slender regions where the future branches sharply, the gravitational keyholes that determine whether an object returns harmlessly or bends onto a much more consequential path. And that is where our journey naturally leads next. Well, when we step from the soft but persistent nudge of the Yarkovsky effect into the realm of what might physically happen to Apophis during its extraordinary passage past Earth, we begin to feel the story-changing tone. And it becomes less about invisible forces drifting across decades and more about the direct, tangible, almost intimate reshaping of a world made of rubble and dust. You see, close approaches are not just encounters in space, they are events with consequences, physical consequences, the kind that my that sear themselves quietly into the future. Um, so, so let us look closely at what might happen to this wandering stone on the night it threads the gap between Earth and its satellites. Um, you see, when an asteroid like Apophis passes this close, the tidal stresses and gravitational gradients we talked about earlier do more than stretch its interior. They also have the power to reshape its surface. And, um, well, this surface reshaping is not a dramatic avalanche or a cinematic explosion. It is something gentler, more granular, more subtle. Think of grains of dust sliding down a slope hardly steeper than a whisper. Think of boulders shifting by centimeters. Think of ridges softening as fine regolith migrates. These movements might be tiny, but they accumulate. They matter. Well, if Apophis is a rubble pile, and the evidence suggests that it is, then its surface is not rigid. It is not frozen stone. It is a world of gravel and rock fragments loosely bound, a cosmic beach where grains range from dust to multi-ton boulders. And when the tidal force interacts with such a surface, it lifts, loosens, and rearranges. A slope that was stable for centuries might suddenly become marginal. A grain of dust might slip into a new resting place. And once a tiny grain moves, the grains above it may follow in slow cascading motion. The models that simulate this kind of internal and surface evolution show something fascinating. Even a small shift on the surface can change the entire thermal behavior of the asteroid. A darker region may be exposed, a brighter patch may be covered, the roughness may increase or decrease. And because thermal properties determine the Yarkovsky effect, and the Yarkovsky effect determines long-term orbital drift, these changes ripple outward like light waves traveling across a quiet pond. But it is not just the surface that might shift. The rotation of the asteroid itself could change. Imagine Apophis turning slowly in the darkness, its spin well measured by telescopes before the flyby. And then, as Earth's gravity stretches it, a moment of torque is applied. Not a strong torque, but a persistent one. And, well, that slight tug might speed the rotation up or slow it down. It might tilt the axis a little. It might cause the asteroid to precess a slow wobbling, like a top losing balance. Well, if the torque is strong enough or the internal structure is weak enough, Apophis might even enter a tumbling state. And tumbling is not just rotation, it is rotation layered with chaos. A tumbling asteroid flips its orientation unpredictably, scattering light in ways that confuse telescopes and warming its surface in patterns that defy simple models. And if Apophis begins to tumble after the encounter, everything from its spin state to its thermal inertia to its long-term trajectory becomes harder to predict. It's not just complexity, but also opportunity. Because if Apophis does tumble, scientists can learn a great deal about its internal structure by observing how quickly the tumbling dampens. A rigid object dampens slowly, a loose rubble pile dampens quickly. So even chaos becomes a source of insight. You see, sometimes people imagine asteroids as immutable, hard, solid, but Apophis is more like a cosmic sand pile shaped by millennia of collisions, by solar radiation, by silent wandering. The flyby of 2029 will be the first time humans witness a rubble pile asteroid experiencing such strong gravitational influence from Earth. And, well, that makes the event not just rare, but scientifically precious. The shape of Apophis might also change. Not dramatically, not in the way movies depict, but subtly. A lobe could relax, a ridge could sag, a cavity might collapse slightly under the stress. Even a 1% shift in the bulk shape would alter the way light and heat interact with the surface. And this 1% shift could amplify across decades. A tiny deformation in 2029 can become kilometers of orbital drift by the time we reach the late 2050s or early 2060s. Well, let us picture the asteroid approaching Earth. It comes in spinning slowly. Its surface is uneven, a mixture of rough and smooth patches, bright and dark materials, boulders and dust. As it nears, Earth's gravity begins tugging on the near side more strongly than the far side. The tug increases, and the asteroid responds. Perhaps its rotation slows slightly. Perhaps internal stresses shift. Perhaps small particles gain just enough energy to begin rolling down slopes. This process continues until closest approach, when the tidal forces reach their peak. The simulations show that during this moment, the forces are strongest not at the equator or the poles, but at certain stress points within the structure. These points may shift material downward or sideways, altering the center of mass. And once the center of mass changes, the rotation changes again. Everything is connected. Everything feeds back into everything else. One of the most intriguing possibilities is what scientists call surface refreshing. This is when older dust is removed or disturbed, revealing younger, less space-weathered material underneath. And, well, if Apophis experiences surface refreshing, its reflectivity could change. Astronomers might observe a slightly brighter or darker object after the encounter. And a new albedo means new thermal behavior. And new thermal behavior means new drift. It is astonishing how a rock can change so much without looking different to the naked eye. The universe is subtle that way. Well, another change that might occur is a shift in the asteroid's spin axis orientation. The axis of rotation determines how sunlight strikes the surface, and the direction of that striking controls heating patterns, and the heating patterns drive the Yarkovsky effect. So a small tilt can alter the long-term path significantly. Think of a marble rolling down a slope. A tiny adjustment at the start sends it to a different place at the bottom, and there is the possibility of resurfacing events. These events happen when the stress causes boulders to shift in clusters. A patch of surface that once had a mixture of fine dust and rocks might become dominated by one or the other. If the dust is removed, the thermal inertia decreases. If dust accumulates, the thermal inertia increases, and either change affects the long-term orbital drift. Interestingly, some simulations suggest that the near miss might even cause Apophis to shed a few small particles, though not large fragments. Small dust plumes or tiny rocks might escape temporarily before falling back or drifting away. These particles, being small and easily influenced by solar radiation, would follow their own tiny trajectories, but they would not pose any threat to Earth. Instead, they provide another window into the asteroid's physical structure. The deeper we look into these models, the more we see that the flyby is not a quiet event. It is an orchestra of small motions, each one playing a role in the decades to come. And if Apophis does change even 1% of its surface characteristics, the amplification across time could lead to uncertainties that stretch far beyond simple prediction. Well, what this means is that the asteroid that leaves Earth's gravitational embrace in 2029 will not be the same asteroid that approached it. not just in motion, but also in structure. Not just in structure, but also in behavior. And that leads us naturally toward another question that scientists have been contemplating for years. What happens if the stresses of the flyby are not just enough to shift the surface, but enough to fracture a part of the asteroid itself? It is not the most likely scenario, but rubble piles are delicate. They can lose small fragments. They can evolve into binary systems. They can shed pieces that follow their own paths. And, well, that possibility opens an entirely new chapter in the story. And that is where our journey leads next, into the realm of fragmentation, where the reshaping of a single world can create many. Well, when we follow the thread from shifting dust and tumbling rotation into the realm of something more fragile, something more precarious, we find ourselves standing before a possibility that scientists do not dramatize but also do not ignore. And that is the possibility of fragmentation. You see, when a rubble pile asteroid like Apophis passes close to Earth, the encounter is not just a dance of forces, but also a test of structural memory, a test of how well thousands of loosely bound stones can hold one another together in the face of gravitational stress. And, well, while the likelihood of major breakup is low, the possibility of partial fragmentation carries weight, because even a small piece breaking off can change the story entirely. To imagine fragmentation, we have to imagine what a rubble pile truly is. It's not a solid mountain drifting through the void. It's a congregation, a pile of rocks gathered by gravity after ancient collisions. The internal structure is irregular. There are hollows and bridges of stone. There are boulders resting against one another in precarious equilibrium. And some of these boulders may weigh tens of thousands of tons, yet they are held in place not by fusion or deep strength, but by geometry, friction, and time. So when Earth's tidal field sweeps across that structure, even gently, some of those internal arrangements may be disturbed. Well, imagine a cluster of rocks inside Apophis shifting under stress. One rock presses harder against another, a cavity narrows, a void collapses. And on the surface, a boulder perched near a ridge might teeter slightly, enough to slip. These small motions do not tear the asteroid apart, but they alter pressures and redistribute weight. Sometimes that redistribution continues, causing a minor chain reaction, a settling event. And occasionally, such an event can create a small crack in the rubble distribution, a weak point, a place where a minor fragment could detach. The idea of fragmentation is not speculative fantasy. We have seen asteroids and comets break apart many times before. Some disintegrate due to thermal stress when passing close to the sunday. Others split after impacts. And a few, like certain comets observed in the past century, fragmented simply under tidal forces as they passed too near a massive planet. So the physics is well understood. A body with low cohesive strength can fracture, and Apophis, if its internal cohesion is low, is not immune to that possibility. But fragmentation is not always a dramatic event. It can be subtle, almost invisible. A small stone the size of a car drifting away, a cluster of gravel slipping off the surface, a pebble cloud dispersing and then fading into space. And, well, even if a small fragment escapes, its trajectory will differ from Apophis, shaped both by the moment of separation and by its own physical properties. That, that is where the story becomes interesting in a more serious way. Because if Apophis were to shed even a single fragment, scientists would then have two objects to monitor instead of one. And the smaller fragment might actually pose a greater hazard someday, not because it is more massive, but because smaller asteroids respond more dramatically to thermal forces, resonances, and orbital drift. A 100-meter or 50-meter fragment experiences a much more pronounced Yarkovsky effect. And the path it takes may diverge significantly from the parent body over the course of decades. You see, space is full of examples where a breakup event led to surprising long-term behavior. Some near-Earth asteroids have small companions, moons that were once part of the main body before slowly drifting away. Some comets split into multiple pieces that followed slightly different orbits, a few eventually approaching Earth closer than the original body ever did. So fragmentation is not dramatic fiction. It is cosmic routine, quiet, slow, but consequential. Well, consider what happens if a small boulder, perhaps a few tens of meters across, detaches during the tidal encounter. At first, it drifts with Apophis, but because its mass is small, solar radiation pushes it more. Because its surface area to mass ratio is larger, heating cycles move it differently. And over time, it might drift into a slightly different orbital resonance with Earth. A difference of kilometers after one orbit becomes tens of thousands after a century. And in rare cases, a fragment might find itself in a trajectory with a non-zero impact probability decades or centuries later. It's not certainty, it's refinement, not alarm, but caution. Scientists consider these possibilities because the universe rewards patience and punishes complacency. The likelihood of a major fragmentation during the 2029 flyby is low. The tidal forces are not strong enough to tear the asteroid apart, but the likelihood of small-scale fragmentation, tiny shedding events, or minor structural adjustments is not negligible. And every adjustment, every shift, every small detachment adds new complexity to the long-term predictions. And, well, what makes this especially important is that rubble piles do not need dramatic triggers to change shape. Gentle vibration, slight torque, or a gradual shift in internal pressure can cause pieces to realign. This is why even asteroids that have not approached planets sometimes show signs of surface sliding or reconfiguration. The solar system is dynamic. Nothing is frozen. Nothing is truly still. Well, let us imagine Apophis after its closest approach. The tidal stresses fade as it moves away. The asteroid begins to relax into a new equilibrium. But sometimes, when a body relaxes, the final settling motion reveals internal weaknesses. A void collapses after the stress is removed. A large boulder shifts late after the peak force, and such delayed motions can lead to small ejections hours or days after the flyby. These delayed shedding events have been observed in other bodies, like comets that do not fragment at perihelion, but afterward when the stresses change direction. You see, fragmentation is not a matter of the asteroid failing. It is a matter of the asteroid evolving. These rubble piles have survived for millions of years by constantly rearranging themselves, by breaking, reforming, shedding small pieces, accumulating dust, and releasing it again. They are dynamic organisms in the geological sense. The real question scientists ask is not whether Apophis will fragment significantly, but whether it could fragment subtly enough to affect long-term modeling. A 5-meter rock lost from the surface would change the mass by a tiny fraction, but the implications for tracking would be more complex. A 50-meter fragment would be easier to detect and track, but would also require its own orbit determination and its own long-term projection. And with each additional object comes additional uncertainty. Well, and beyond the scientific challenge, fragmentation also touches a deeper philosophical thread running through the entire story. We grow older, clocks tick, and we imagine the universe as a place of stability. But rubble pile asteroids remind us that stability is often just a temporary arrangement of matter, a balance that can shift with the gentlest push. And nothing illustrates that fragility better than a close planetary encounter. When comets like Shoemaker-Levy 9 broke apart under Jupiter's influence, the fragments followed trajectories that told astronomers more about tidal forces than any equation could have alone. Each piece became a test particle, a messenger, revealing the mathematics of gravity in real time. And in the same way, if Apophis were to lose even a small fragment, scientists would gain unprecedented insight into the cohesiveness, internal friction, and dynamical response of rubble piles. The knowledge gained would be invaluable, not because of danger, but because it improves our understanding of near-Earth objects as a whole. Thousands of such bodies wander near Earth. Many are rubble piles. Many are poorly understood. Apophis is one of the best studied among them. If it teaches us how rubble piles respond to close encounters, that knowledge stretches outward to hundreds of other bodies we track. Well, there is another layer to fragmentation worth exploring. If Apophis were to lose material, even a little, that material could form a temporary debris trail. Tiny particles could drift in the asteroid's path. And while such debris would not threaten Earth, it could offer scientists a rare chance to study how small regolith behaves in microgravity, the way dust disperses, the way sunlight pushes it, the way it interacts with the parent body's weak gravity. These processes are poorly understood and incredibly important for future missions involving landers or asteroid deflection technologies. You see, every small piece that leaves an asteroid becomes a natural experiment. It tells us how bodies evolve. It tells us how they fail. It tells us how they hold together. And, well, if Apophis sheds even one grain visible to our instruments, that grain becomes a data point in a cosmic puzzle we have been assembling for decades. So fragmentation is not the catastrophic scenario people imagine. It is not Hollywood. It is geology. It is physics. It is the slow rhythm of rubble piles adjusting to forces that have shaped them since the dawn of the solar system. And if Apophis participates in that rhythm as it passes Earth, even subtly, we will gain knowledge that reshapes our understanding of near-Earth objects. And that brings us to the next crucial link in the chain of prediction. Because fragmentation, shifting surfaces, changing rotations, and evolving Yarkovsky forces all influence one critical aspect of the asteroid's future: how it interacts with gravitational keyholes. Those narrow corridors in space where even the smallest deviation can send a body onto a trajectory that returns decades later. And that is where our path leads next, into the strange and delicate geometry of gravitational keyholes, where fate is measured not in kilometers but in meters, and where the future of an asteroid can hinge on the subtlest of cosmic nudges. Well, When we step from the fragile possibility of fragmentation into something even more delicate, even more mathematically slender, we find ourselves standing before one of the most quietly dramatic concepts in celestial mechanics. And that is the idea of gravitational keyholes. You see, if tidal forces shape the body of Apophis, and if fragmentation reshuffles its mass and surface, then gravitational keyholes are the narrow gates through which the asteroid's future must pass. And, well, these gates are not wide cosmic corridors. They are tiny, sometimes only a few hundred meters across, floating invisibly in space like threads in a vast gravitational tapestry. So when we talk about Apophis passing Earth in 2029, we are not just talking about a near miss. We are talking about a journey through a landscape of invisible doorways. A gravitational keyhole is a region in space where the gravitational pull of a planet alters the trajectory of a passing object in just the right way to send it into a future orbital resonance. And a resonance means that the asteroid returns to the same relative position on a later orbit. If that timing aligns with Earth's own orbit, the asteroid may return on a collision path decades or centuries later. So a keyhole is not where an impact happens. It is where an impact decades later becomes possible. That is why scientists treat these minute regions with such seriousness. Because even though they are small, even though the asteroid passing through one is unlikely, the consequences of such a passage stretch forward deep into the future. Well, the most famous keyhole associated with Apophis was the one predicted for the year 2036. When the asteroid was first discovered, before its orbit was well refined, calculations showed a tiny keyhole that Apophis could pass through during its 2029 flyby. And if it passed through that region, its next encounter with Earth 7 years later would be catastrophic. That possibility led to headlines, concern, a flurry of research. But as more data came in, the predicted orbit sharpened, and scientists ruled out the 2036 keyhole entirely. You see, that early scare taught us something about the importance of precision. A shift in measurement by only a few hundred meters changed the prediction entirely. And, well, that is the nature of keyholes. They are small, narrow, delicate, and they are sensitive to the slightest change in trajectory. When a rubble pile asteroid with evolving surface properties approaches Earth, predicting whether it will pass through or near a keyhole becomes an exercise in understanding every possible force acting on it. The 2036 keyhole was the one the world heard about. But gravitational modeling reveals many more. Some are for later dates, some are for different orbital configurations, and because the orbit of Apophis is sensitive to tidal forces, thermal drift, rotational changes, and potential fragmentation, the size and location of these keyholes after 2029 may shift. Well, imagine an asteroid approaching Earth along a specific path. Now imagine that path as a line, and somewhere along that line is a tiny corridor, maybe 200 or 300 meters wide, where Earth's gravity would bend the asteroid just enough to bring it back for a future rendezvous. And imagine that everything we discussed earlier, tidal deformation, boulder shifting, tumbling, dust migration, could nudge that line slightly, not dramatically, not violently, but just enough to change whether the asteroid misses the keyhole or grazes its edge. It's not certainty, it's refinement. It's not drama, but geometry. And that geometry can be incredibly unforgiving. Um, uh, what makes all this even more fascinating is that keyholes are not fixed features. They depend on the exact orbital configuration of both Earth and the asteroid at the time of the encounter. They drift, they stretch, they shrink. A slight change in the asteroid's velocity at closest approach can shift the location of a keyhole by kilometers. And if the asteroid's rotation changes its thermal drift afterward, the future orbital resonances change too. So, so the keyholes predicted before 2029 are not necessarily the same keyholes that will exist after it. Well, scientists model these keyholes using Monte Carlo simulations, generating millions of hypothetical apophyses, each with slightly different physical properties. And, um, well, across these millions of simulations, certain regions of space emerge as sensitive, regions where small uncertainties lead to dramatically different outcomes decades later. These are the gravitational keyholes. They are like the hinges on which the future turns, delicate and often invisible until the calculations reveal them. You see, the Earth is not just a passive observer when Apophis passes by. It acts as a gravitational lens. Objects that pass behind Earth relative to the Sun are bent one way. Objects passing in front are bent another. The exact angle, the exact distance, the exact timing determine whether the asteroid leaves the encounter, shifted by millimeters per second or by centimeters per second. And those small differences decide whether it drifts harmlessly through space or wanders near a keyhole. The idea that Earth can redirect an asteroid's path so precisely is humbling. It shows how connected everything is. We grow older, clocks tick, and we imagine celestial mechanics as something majestic and overwhelming. But sometimes celestial mechanics comes down to a matter of meters, a matter of seconds, a matter of which way a warm boulder faced when it radiated heat into space. Well, when Apophis approaches Earth, it will enter a volume of space filled with hundreds of potential gravitational resonances. Most of these will lead nowhere. They are harmless. They scatter the trajectories across decades in normal, predictable ways. But a few of them, only a few, channel the asteroid into long-term evolutionary paths that come close to Earth again. And those few are the ones scientists track most carefully. The existence of keyholes is not a sign of danger. It is a sign of the precision required to understand a world in motion. That is why scientists emphasize updated tracking after the flyby. They know that Apophis's surface might shift. They know the Yarkovsky effect might change. They know the assumptions that generate current orbital models may no longer apply in the same way. And so they prepare to measure everything again. Well, let's imagine what happens if Apophis passes slightly above a keyhole. In that case, it continues harmlessly along its path. The future predictions continue to show no impact scenarios, and the asteroid remains just another near-Earth object. But imagine it passing slightly below, a shift caused by a surface landslide or a small fragment detaching. That tiny deviation could place the asteroid on a path where the gravitational pull at closest approach redirects it onto a resonant orbit. And, well, that changed orbit might intersect Earth's position decades later, not because of intention, not because of risk overlooked, but because a pebble moved, or sunlight warmed a patch of surface differently, or the asteroid tumbled instead of spinning smoothly. It reminds us that the future is sensitive to the smallest details, that cosmic events unfold on scales, vast and tiny at the same time. One of the most striking examples of how keyholes matter comes from an asteroid called 4596 Rota. A tiny shift during a close approach altered its resonance state, changing its long-term orbit significantly. And the same has been seen in comets and smaller asteroids. So Apophis is not unique, but it is one of the largest objects we have studied in such detail as it prepares to pass so near. Well, another intriguing part of the story is how fragmentation interacts with keyholes. If Apophis sheds even a small fragment, each piece has its own set of potential keyholes. A small fragment, being more influenced by thermal drift, could wander into a keyhole that the main body would have missed entirely. And while scientists would track such fragments if they existed, their small size could make them harder to observe early on. That adds complexity, it adds variables. Not danger in a dramatic sense, but uncertainty in a scientific sense. You see, keyholes symbolize this interplay between the deterministic and the chaotic. The deterministic says gravity follows rules. The chaotic says tiny uncertainties grow. And, Apophis stands at the intersection of these truths as it approaches Earth. The reason keyholes matter is not because we expect Apophis to pass through one. The current models show no such scenario. But because once the asteroid is reshaped by tidal forces, thermal effects, or possible fragmentation, the location and relevance of keyholes will shift. And the safest predictions for the decades after 2029 will come only from updated measurements. Well, in a strange way, keyholes are poetic. They are like tiny doors suspended in space, doors that lead not to danger but to diminished uncertainty. If we know where they are and whether Apophis avoids them, we know something deep about the stability of the asteroid's future. And that leads us naturally into an even subtler landscape, because once we talk about keyholes and sensitivity, we find ourselves drawn toward the very heart of chaos in celestial mechanics. The realization that predicting 5 years is one thing, predicting 50 is another, and predicting a century is like trying to predict the shape of a cloud by watching a single swirl of vapor. And that is where the story takes us next, into the realm where the tiniest initial differences grow into vast uncertainties, where tumbling spin states and shifting centers of mass create clouds of possible futures rather than a single line. And, that brings us gently into the domain of chaos itself.